Like the unseen conductor of a great orchestra, an operating system keeps every part of your computer in delicate synchrony. From the smallest keystroke to the most complex calculation, it quietly orchestrates an elegant dance of data and decisions, all behind the scenes. Tonight we'll wander gently through this hidden world, not to study for an exam, but to appreciate the thoughtful patterns and quiet intelligence woven into the systems we use every day. Welcome to Byte and Night. Let the gentle sounds soothe your mind as we drift into the beautiful logic of computer science. Imagine stepping into a grand old library. The shelves are lined with books, each filled with potential, ready to teach, to entertain, to inform. But without a librarian to sort, to guide, to manage the quiet hum of activity, chaos might slowly creep in. The operating system is your computer's librarian, calm, tireless, and invisible. It doesn't just manage, it brings order to the potential within every machine. At its heart, an operating system is a quiet mediator between the person using the computer and the complex, chattering machinery inside. You press a key, you click a file, you launch a program. What happens next might seem simple, but under the surface, the operating system begins a cascade of carefully orchestrated events. It opens the right door, moves the right data, grants the right permissions. It makes sure each program has just the resources it needs, no more, no less. You might think of the operating system as the backstage crew in a peaceful theater. While the audience focuses on the actors, the apps, the games, the websites, the crew is constantly working. Lights dim at the right moment, curtains rise on cue, microphones hum to life. Without the operating system, none of this would unfold so smoothly. One of the fundamental roles of an operating system is resource management, but not in a frantic juggling way. It's more like a thoughtful host at a dinner party. Each guest, be it a program or a background task, has a seat. Some guests arrive hungry for attention, others are content to wait their turn. The operating system listens, balances, and serves. It manages the CPU's time, allocates memory, controls access to devices like printers or cameras, and ensures everything flows in harmony. There's also a quieter duty, often unnoticed: abstraction. The operating system gently hides the rough edges of hardware from the user. You don't have to know how many milliseconds your hard drive takes to retrieve a file, or what voltage your processor needs to perform a calculation. Like a translator between two very different worlds, the OS speaks the language of both silicon and humans. Over time, many types of operating systems have taken the stage, each designed for a particular environment. There are the general-purpose systems we know well: Windows, Mac OS, and Linux, built for laptops, desktops, and servers. These are like friendly generalists, capable of doing many tasks, from word processing to rendering complex graphics. But not all operating systems live on screen-lit desks. Some are embedded quietly tucked inside washing machines, smart thermostats, or car engines. These embedded systems don't need to do much, but they must do it with absolute reliability. They are like devoted specialists, small, efficient, and focused. There are also real-time operating systems. These are built not just for precision, but for punctuality. In a medical device or an aircraft control system, a single delay could be costly. These operating systems are designed with one quiet promise: to respond within strict timing constraints, no matter what. And then, there are distributed operating systems. Imagine a group of computers working together across a network, behaving like one unified machine. The operating system in this case doesn't just manage a single CPU or disk, it coordinates across many. It smooths out the illusion that the resources are far away. Everything feels close, shared, and unified. As we look back in time, the evolution of operating systems tells a slow and thoughtful story. In the early days of computing, there was no operating system at all, just people, punching cards and flipping switches, feeding instructions directly into massive machines that filled entire rooms. It was a patient process, laborious, and full of anticipation. Then came batch systems in the 1950s and 60s, machines that could process a queue of jobs, one after another, without human intervention. It was like posting letters in a box and waiting for them to be delivered. You didn't interact with the computer in real time, but the pace was steady and reliable. Later, time-sharing systems arrived, bringing with them a sense of immediacy. For the first time, many users could interact with a single computer at once, each feeling like they had it to themselves. Like an attentive teacher rotating between students, the system gave each user a moment of focus before moving on to the next. This gradual march brought us into the modern age of graphical interfaces and multitasking. The operating system became not just a manager, but a companion, handling windows, icons, cursors, and touchscreens. It listened as we typed, it responded as we swiped, and all the while it quietly maintained the harmony beneath the surface. Even today, the story continues. Operating systems now live in the cloud, on our wrists, in our cars, and in tiny sensors sprinkled across our cities. They learn, adapt, and sometimes even update themselves while we sleep. It's easy to forget how much they do, because a good operating system is almost invisible. It doesn't ask for thanks. It doesn't need the spotlight. It's there, quietly guiding the symphony of tasks, letting everything else shine. So as we drift through this quiet forest of computation, remember that there is always a gentle hand at the wheel, one that turns complexity into simplicity, noise into order, and raw power into possibility. Imagine standing in a quiet train station at dawn. Trains come and go, each following a careful schedule, each with its own destination, its own story. In the world of operating systems, these trains are called processes. And the station, the one that oversees their arrivals and departures, keeps them from colliding, and ensures everything moves in order, is the operating system itself. At its most gentle definition, a process is simply a program in motion, a running instance, a living thing in the soft mechanical sense. You might write a program, a simple calculator or a browser, but it's not a process until it's given life by the operating system. When you double-click or tap or open, that's the spark. The process begins to breathe. Each process carries its own little universe. It has memory set aside just for it. It keeps track of its own instructions, its own variables, its own version of the world. The operating system, ever the thoughtful caretaker, ensures these little universes don't bump into each other. It builds invisible walls so one process can't accidentally or intentionally read what another is doing. Each train runs on its own track. Processes don't last forever. Like moments, they arrive, they do their work, and then they fade away. This journey is called the process lifecycle, and it's more poetic than it sounds. A process begins in the new state. It's just been created. Maybe you clicked an icon. Maybe a background task was scheduled to start. The operating system, like a gentle hand, prepares everything the process needs. It's not running yet. It's waiting in the wings. Once ready, it moves into the ready state. This is a kind of quiet anticipation, like a performer waiting just off stage. The process is prepared, eager, holding everything it needs. But the stage, the CPU, is still busy with another act. When its turn comes, the process enters the running state. Now, the spotlight is on. The CPU gives it full attention, executing its instructions, step by careful step. This might last a few milliseconds. It might stretch longer, but eventually the process will pause. Maybe it's waiting for a file to load or for input from the user, and so it moves to a waiting state. While it waits, the operating system turns to others in line. The CPU is never idle for long, and when the waiting ends, when the file is ready or the button is pressed, the process moves back to ready, and the cycle continues. Finally, when the process has done what it came to do, it enters the terminated state. The curtain falls. The memory it used is cleaned up. The resources are returned to the system. It slips away quietly, like the last whisper of a dream. Now, just as every traveler carries a passport, every process carries something called a process control block, a small but vital record kept by the operating system. This block holds the essence of the process's identity. Inside, you'd find its process ID, a unique number like a name tag. There's a record of what the process was doing, what instruction it was about to execute, where its memory starts and ends, what files it's using, what it's waiting for. If the process is paused, the control block holds a kind of snapshot, so it can return and pick up right where it left off. You might picture the process control block as a tidy folder in a filing cabinet. When a process is paused, the operating system places its folder gently back into the drawer. And when it's time to resume, the folder is pulled out, opened, and the story continues seamlessly. It's easy to think of a computer as doing one thing at a time, but in truth, it's often juggling dozens, even hundreds of processes at once. Some are familiar: your browser, your music player, your email. Others hum in the background, checking for updates, managing your keyboard, syncing your files. The operating system uses a graceful dance of scheduling, priorities, and timing to give each process a turn. It all feels smooth on the surface because underneath, every step is choreographed. And unlike a human juggler, the operating system never tires. It remembers every pause, every detail, every instruction. It holds the rhythm, even in moments of chaos, even when memory runs low or the power flickers. Processes come and go, but the operating system remains, a quiet guardian, watching over each little life that flickers into being and fades away again. So tonight, as your thoughts slow and your breathing settles, know that within your device, 1,000 tiny journeys are unfolding. Each process, brief but complete, each guided gently from creation to conclusion. Not rushed, not forgotten, just part of a soft and endless flow. As our journey through processes gently winds down, we notice something curious. One process, moving steadily through its life cycle, feels like a single, clear melody. But in today's computers, that melody often splits into harmonies. Several voices working in concert, not just one. A single process, it turns out, can contain many threads of thought, running together, taking turns, building something greater than one step at a time. This brings us into the intricate world of threading and concurrency, where activity is not just sequential, but shared. Not rushed, not chaotic, but carefully layered, like several hands working together in a quiet room. A thread is like a single line of action within a process. If the process is a story, the thread is a character following one path through the plot. And a process can have many threads, each one doing its part, each one advancing the work. They share the same space, the same memory, the same files, but each has its own task, its own rhythm. This is multi-threading, a design where a single process is divided into multiple threads, each performing a smaller job. Imagine a painter who doesn't work alone. One hand sketches the outline, another fills in color, a third adds texture. Each thread is still part of the same artwork, the same goal, but they divide the labor to finish more smoothly, more swiftly. But here's something important. In most systems, there's only one set of hands, the CPU. So how do multiple threads appear to work at the same time? The secret lies in something called context switching. The operating system gently pauses one thread, remembers exactly what it was doing, and turns to another. It repeats this many times a second. To us, it feels like parallelism, but in truth, it's a fast, quiet rotation. Each thread getting a turn, each step remembered, none left behind. Imagine a librarian helping 3 readers at once. She walks to one, answers a question, then moves to the next. She holds each conversation in her mind, picks up where she left off, and never seems rushed. That's what the operating system does with threads, switching smoothly, quickly, without losing the thread of the story. But as you might imagine, sharing the same space comes with risk. When multiple threads touch the same data, like cooks using the same bowl or hands writing on the same page, mistakes can creep in. 2 threads might update a value at the same time. One might read information while the other is halfway through changing it. These subtle timing errors are called race conditions. A race condition happens when threads race to access a shared resource, and the result depends on who arrives first. It's not a crash, it's something quieter. A flicker of wrong behavior, a number that doesn't add up, a file that saves incorrectly. These bugs can be rare, hard to reproduce, and difficult to find, like trying to spot a bird only seen at sunrise on a windy day. To prevent this, the operating system and the software itself uses synchronization. These are soft rules, gentle barriers that make threads wait their turn when sharing something important. The simplest form is a lock, often called a mutex, short for mutual exclusion. When a thread reaches a critical section of code, it checks for a key. If it has the key, it proceeds. If not, it waits. When it finishes, it returns the key for others. Like a restroom with only one stall, the lock ensures privacy. There are also semaphores, a kind of counting lock. Instead of just one key, there are a few. If only 3 threads should access a resource at once, then only 3 keys are handed out. If all are in use, new threads wait. It's orderly. It's fair. and it helps avoid crowding in places where too much activity would cause confusion. Sometimes threads wait for a particular event. Maybe they need a file to finish loading or a message to arrive. In these moments, condition variables come into play. They're like soft signals. Not yet, they whisper. And later, now, you may continue. Of course, synchronization must be used with care. Two threads might each wait for the other's lock, forming a deadlock, like two people in a narrow hallway, stepping aside for each other, but neither moving forward. These are the still moments when everything waits and nothing proceeds. But when threading is handled well, it becomes invisible. You browse the web while music plays, while downloads continue, while notifications appear, each managed by threads, switching gently in the background, orchestrated by the operating system's quiet grace. So tonight, as your thoughts slow and the world outside dims, remember the threads still moving within your device. Not in conflict, not in chaos, but in soft coordination, each one doing its part, each one yielding and resuming. It's a lullaby of logic, a peaceful web of activity. And in the center, always watching, always guiding, is the operating system, keeping the threads from tangling so the story can unfold. As we drift onward through the gentle machinery of threads and their careful synchronization, a new question quietly emerges. When many threads or processes are ready to run, each waiting, each hoping for a moment of attention, how does the CPU decide who goes next? After all, the CPU is just one, a single tireless worker at the center of everything, and yet it must serve many. It must choose, not in haste, but with balance, fairness, thought. This silent art of decision-making is known as CPU scheduling. You can imagine it like a soft-spoken host at a bustling tea house. Guests arrive, each needing just a few minutes to be served. Some are patient, some in a rush. Some have been waiting quietly for some time. The CPU scheduler is that host. It looks at the queue and gently selects the next guest, always with a reason. Let's begin with the simplest form of scheduling. First come, first served, or FCFS. As its name suggests, it serves processes in the order they arrive. No reordering, no rushing, just a patient line like people waiting for a bus. The first one to arrive is the first one to board. This is simple, predictable, and sometimes even comforting. But FCFS isn't always kind. Imagine a long task arriving before a short one. The short task must wait, even if it would have taken only a few moments. The line stays fair, but the overall wait grows longer. It's a queue with no flexibility, honest but sometimes inefficient. So another strategy steps in. Shortest job first, or SJF. Here, the operating system chooses the process with the smallest expected burst of activity. It's like letting someone with a quick question go ahead in line. The total wait time often shrinks, efficiency improves, but there's a cost. The scheduler must somehow guess how long each process will take, and if it's wrong, the whole rhythm stumbles. SJF, though elegant, can be unfair. If short tasks keep arriving, longer ones may wait, and wait, and wait. This is known as starvation, like a traveler at the back of the line who's never quite next, no matter how long they stand. To help ease this, many systems use a friendlier method called round robin. Here, each process gets a small slice of time, a time quantum. When its time is up, the next process takes over. And when the circle is complete, the first process gets another turn. It's like passing a talking stick in a gentle circle. Everyone gets a voice, even if just for a little while. Round Robin is fair and responsive, especially in environments where users expect quick feedback. A game, a browser, a chat window, none are forgotten for too long. But if the time quantum is too short, the system spends more effort switching than actually working. If it's too long, the feeling of responsiveness fades. Now imagine the scheduler with a little more knowledge, knowing not just who arrived first or who's quickest, but who's most important. This brings us to priority scheduling. Here, each process is assigned a priority, like a gentle ranking. The scheduler chooses the process with the highest priority, regardless of arrival time or length. This allows urgent tasks, perhaps system updates or real-time actions, to take precedence. But again, we meet the shadow of starvation. Low-priority processes might wait too long if high-priority ones keep coming. To soften this, the operating system may use aging, a quiet increase in a process's priority the longer it waits. Eventually, even the quietest voice is heard. Each algorithm has its own strengths. FCFS is honest, SJF is efficient, Round Robin is fair, priority scheduling is flexible. Often, systems use a mix, blending strategies, adjusting based on context, always searching for harmony. What's most remarkable is that all this happens invisibly. As you type, scroll, and listen, your system makes these choices again and again, thousands of times a second. It weighs the cue, picks the next, gives each task its moment, then moves on. There is no rush, only rhythm, and so the CPU, this small glowing center of your device, continues its quiet work, choosing, serving, balancing needs. Never still, never overwhelmed, because the scheduler is there to guide it, like a conductor with a baton, giving each note its place in the score. Tonight, as your thoughts slow and your body settles, know that deep inside your computer, the scheduler carries on, calm, steady, and fair. A quiet keeper of order, ensuring that no process is forgotten, and that every task in time has its turn. As the CPU rhythmically dances through processes and threads, guided by quiet algorithms that decide who speaks and when, another silent structure supports this flow: memory. Memory in a computer is a kind of soft surface where everything plays out. The words on your screen, the buttons you click, the sound that reaches your ears, they all pass through memory, briefly resting there as the system brings your instructions to life. But unlike a blank canvas, memory is limited. It must be shared delicately and fairly between many tasks and ideas. And this is where memory management begins, an invisible art performed by the operating system to make sure every process has just the space it needs, exactly when it needs it. You can imagine it like a peaceful inn with many rooms and many travelers. Some stay briefly, others take longer. Some need quiet corners, others want space to spread out. The operating system is the innkeeper. It decides who stays where and for how long. It makes sure no one overlaps, no one is lost, and everyone has what they require. One way the system manages this is through paging. Instead of treating memory as one long strip, It divides it into small, fixed-size pieces called pages. Like numbered tiles in a mosaic, these pages can be moved around, rearranged, or reused. Every process, in turn, has its own set of pages. But these pages don't have to sit side by side. They can live anywhere in physical memory. The operating system keeps a tidy list, a page table, so it always knows where each page is. This allows processes to use memory without needing one continuous stretch. It's flexible, efficient, and quietly powerful. There's also another approach known as segmentation. Instead of breaking memory into equal pages, segmentation divides it into logical parts, like chapters in a book. One segment might hold the code, another the data, another the stack. Each segment is different in size, shaped by its content. This can be more intuitive for a program as it mirrors how software is structured. But it also means managing pieces of different shapes, which can be more complex. Now imagine a moment when memory is full, new processes arrive, others grow, but there simply isn't enough space for everything at once. Should the system stop? Should it refuse? Instead, the operating system offers something magical: virtual memory. Virtual memory is the promise that each process can have more memory than physically exists. It's like a deep drawer with a false bottom. Behind the scenes, the system stores some pages temporarily on the hard disk, freeing up space for new ones. When a process needs a page that's been set aside, it's quietly brought back. This is called a page fault, a small bump in the rhythm. But handled smoothly, the process never even notices. This illusion, that memory is vast and uninterrupted, is one of the great achievements of operating system design. It allows modern software to stretch out, grow, and breathe, even on modest hardware. Of course, deciding how to assign memory is a challenge in itself. This brings us to allocation strategies, the methods used to find the right fit for each request. One simple method is first fit. The system scans memory and gives the process the first available block that's big enough. It's quick, but can leave tiny unused spaces scattered around, like mismatched puzzle pieces. Another is best fit. The process is given the smallest block that works, reducing waste. But finding the perfect fit takes time. Then there's worst fit, which uses the largest available block, hoping to leave behind useful leftovers. Each method has its trade-offs. Some are faster, others more efficient. Some better suited to long-running systems. Over time, memory may become fragmented, full of small gaps too scattered to be useful. The operating system may need to shuffle things, like a careful librarian reorganizing books to make room for more. This rearranging can be quiet and invisible, or sometimes it may pause the system briefly to restore order. And throughout all of this, the operating system watches. It tracks what's been used and what's free. It ensures that one process cannot see another's memory, preserving both privacy and safety. It balances the needs of the many, constantly adjusting, constantly rebalancing. So tonight, as your thoughts begin to scatter like soft pages drifting in the wind, remember that within your device, memory is being shaped and reshaped with care. Pages are mapped, segments are tracked. The illusion of infinite space is carefully maintained by a quiet intelligence that never sleeps. Memory may seem invisible, but it's always there, holding the shape of your thoughts, the state of your apps, the story of your session. A soft, structured space, kept in harmony by the operating system's gentle hand. chapter exploring the delicate spaces of memory, where data lives briefly, moves swiftly, and fades when it's no longer needed, we now step into something more lasting. A quieter place. A digital library where the stories don't vanish when the power flickers. This is the realm of file systems and storage. Think of a file system as a peaceful archive, shelves lined with information, drawers labeled and sorted. Every photo you've taken, every document you've typed, every song you've saved, they all live here, carefully tucked away until they're needed again. At the heart of this system is the file, a small container of data. It might be a poem, or a spreadsheet, or a piece of music. But a file is more than just data. It's also a promise that what you create will still be there tomorrow, exactly as you left it. To keep files organized, the operating system builds directories, or folders. These are like labeled boxes, each one holding a group of files. Some directories contain just a few items. Others branch and nest into deep structured trees. You might imagine a parent directory holding children, each of whom may be parents themselves. It's a quiet, familial structure, a way to keep everything in reach without letting it become a mess. When you open a folder or search for a document, you aren't combing through all the data on your disk. Instead, the operating system consults a kind of map. This map tells it where each file begins, how large it is, when it was last opened, and who's allowed to access it. This hidden layer of information is called metadata. Metadata is like a file's personal diary. It knows when the file was born, its creation date. It remembers every visit, each time it was opened or changed. It holds its name, its size, and its permissions. All of this is kept separate from the file's actual contents, making it quick and easy for the system to answer your requests. But behind the folders and names, files are not stored like books on a shelf. They are broken down into blocks, small, fixed-sized pieces, scattered across your storage device. It might seem messy, but it's actually efficient. When you save a large file, it can fill the gaps left by smaller, deleted ones. Like pouring water into oddly shaped containers, the system fills the spaces, making the most of what it has. And yet, accessing these pieces in the right order at the right time is an art in itself. That's where disk scheduling comes in. Inside many storage devices, especially traditional hard drives, data is read from spinning platters. An arm with a sensor moves across the surface, like a record player's needle. But moving this arm takes time. So the operating system chooses carefully which request to serve first and which can wait a moment longer. One simple approach is first come, first served, honoring the order in which requests arrive, but this can be inefficient. If the first request is at one end of the disk and the next at the other, the arm may travel back and forth unnecessarily. To improve this, the system may use the shortest seek time first strategy, serving the request that's physically closest. This reduces movement and speeds things up, but it can leave far-off requests waiting too long. Then there's scan, often called the elevator algorithm. Like an elevator moving floor by floor, the arm sweeps in one direction, serving requests as it passes them, then turns around. This provides fairness, avoiding the problem of starvation. Everyone gets their turn, eventually. In modern systems, many of these concerns are hidden away by solid-state drives. With no moving parts, data can be accessed in near-instant time from anywhere. But the logic behind disk scheduling still matters, because even in fast systems, efficiency and order keep everything smooth. And all of this, the structure, the metadata, the scheduling, is handled by the file system. Different systems use different formats: FAT, NTFS, ext4, APFS, each with its own way of organizing blocks, tracking changes, and protecting data. But the purpose is always the same: to preserve, to organize, to serve. You rarely think about your file system, and that's exactly the point. It's meant to be invisible. You click a file, and it opens. You save something, and it stays. But beneath that simplicity is a quiet precision, a layered architecture built to keep your digital life intact. So tonight, as you drift deeper into rest, know that within your device, the archives remain in perfect order. Files rest where they belong. Metadata whispers, reminders of their past. And when the time comes, the operating system will know just where to look, bringing your thoughts, your memories, and your work back into the light. In a world that's always moving, the file system is your device's memory palace, silent, structured, and always ready. So far, we've wandered through memory and files, pages and schedules, internal rhythms that shape how a system thinks. But there's another conversation happening, one that reaches beyond the processor and touches the outside world. It's quieter, subtler, but essential. It's the exchange between your device and everything connected to it. This is the domain of input and output systems, or simply I/O. When you move a mouse, press a key, touch the screen, or hear a sound, the computer responds. But it doesn't do so directly. The operating system doesn't speak the same language as your printer, your camera, or your speakers. It needs a translator. A quiet, loyal intermediary that knows the details of each device. These are called device drivers. A device driver is a small piece of software written to understand a specific piece of hardware. It knows how to talk to a particular printer, or camera, or keyboard. The operating system doesn't need to know how a certain brand of speaker plays sound. It simply asks the driver to handle it. And the driver, in turn, performs the exact sequence of steps needed to make the device respond. You might think of drivers as tour guides. Each one speaks the local dialect of a specific device, guiding the operating system through customs, quirks, and protocols. The driver shields the rest of the system from complexity, allowing everything to flow smoothly. But input and output don't always happen instantly. Some devices are slower to respond. Others provide more data than the system can handle at once. To bridge these gaps, the operating system uses a gentle pause, a resting place where data can wait just for a moment. This is called I/O buffering. An I/O buffer is like a waiting room. When data arrives, perhaps a stream from a microphone, it's stored temporarily in a buffer. The operating system takes from this buffer at its own pace, keeping everything in order. Likewise, when writing data to a device, like saving a file to a disk, the system might place it in a buffer first, then write it out gradually. This makes everything feel more fluid. No pauses, no interruptions, just a smooth, continuous flow. Buffers absorb delays and soften the edges between fast and slow. But sometimes something must be noticed immediately. A key is pressed, a flash drive is removed, a device finishes its task. In these moments, the system can't afford to check constantly. Instead, it waits for a signal, a soft tap on the shoulder. This is called an interrupt. An interrupt is a message sent from a device to the processor saying, "I need your attention." When it arrives, the operating system pauses what it's doing, just briefly, saves the current task, and handles the interrupt. It's a delicate interruption, not a disruption. Imagine writing a letter when someone gently knocks at your door. You set down your pen, open the door, speak for a moment, then return to your sentence. That's how the system treats interrupts. Calm, respectful, focused. There are many types of interrupts. Some are from hardware, like a mouse click or a timer expiring. Others come from software, perhaps a program finishing a task or requesting something urgent. Each interrupt has a priority. Some are answered right away, others are placed in line to be handled soon. To manage these, the operating system uses a structure called an interrupt vector table, a kind of phone book that matches each interrupt to the correct response. When the interrupt comes, the system looks it up, finds the right handler, and steps into action. And once the interrupt is handled, the system doesn't forget where it left off. It restores the paused task, picks up the memory it saved, and continues as if nothing ever happened. Together, device drivers, I/O buffering, and interrupt handling form a soft bridge between the computer and the outside world. They allow input and output to happen without confusion, without delay, and without needing the system's full attention every second. Whether it's saving a document, printing a page, recording your voice, or playing a song, the operating system quietly listens and responds. It coordinates dozens of devices, each with its own pace and voice, and it does so without ever raising its own. So tonight, as your body rests and the room grows still, know that your device continues to listen. It waits for taps and signals. It receives and responds. And beneath it all, the operating system remains alert, managing buffers, translating languages, and gently handling each interrupt with care. It's a soft, mechanical mindfulness, a steady presence ensuring that every connection works, every click is heard, and every silence is understood. As we near the end of our quiet journey through the world of operating systems, we come to a final, protective layer, one that wraps around all the others like a soft blanket. Memory, files, processes, and schedules, they all depend on something deeper. Trust. Trust that the system will stay whole, that your information is safe, that nothing will reach where it shouldn't. This is the quiet work of security and protection, the system's way of not only serving, but safeguarding. It begins with a question. Who are you? Not in a grand or philosophical way, but in the simple sense of identity. When you wake your device, tap a password, or scan your fingerprint, you're taking part in user authentication, a gentle ceremony of recognition. Your device doesn't know faces or voices on its own. It learns through patterns, through stored credentials, through small digital promises. Once those are confirmed, the door opens. And from that moment forward, your identity travels with you, guiding what you can touch and what stays out of reach. That's where access control comes in. A quiet set of permissions, drawn in soft lines. This file is open to read. That one is locked away. One program may listen to music, another cannot reach the camera. Every decision is small, thoughtful, and done without drawing attention. Even within the system, programs are treated with care. Each process is watched gently to make sure it doesn't reach too far. No one process can read another's thoughts. No app can wander into a memory that doesn't belong to it. These boundaries aren't loud or sharp, but they are firm, and they're always there. The system keeps records too, audit logs, where it notes each login, each denied access, each attempt to change something important, not to accuse, but to remember. These records can help rebuild what was broken or explain what was misunderstood. They are the diary of the system, honest, quiet, and faithful. And deeper still, the system guards itself. It uses integrity checks, verifying that its own parts haven't been changed without permission. Secure Boot begins the day with a self-exam. Am I still me? It asks softly. Am I still whole? If something seems wrong, if a process behaves strangely, or a file changes too quickly, the system may respond. Through anti-malware tools, through sandboxing, through quiet containment. These aren't acts of fear, but of care. The operating system protects not just your data, but your experience, so that it remains smooth, responsive, and trusted. And perhaps the most beautiful part of all this is how little you need to think about it. The protection is built in. It's always listening, always watching, always remembering. Not with suspicion, but with steady presence. Security isn't about walls, it's about boundaries drawn with purpose. It's about ensuring that everything and everyone can move freely within their space, without fear, without interference, without risk. And so, as we close this final chapter, you might pause and reflect on the quiet elegance beneath your fingertips. The operating system, so often invisible, has been there all along, managing, balancing, protecting. You began this journey with a simple curiosity, and now, having gently explored the inner harmony of processes, threads, memory, and beyond, you've seen what few take time to notice: the graceful intelligence inside the machine. And now, like the final lines of a poem or the soft closing of a well-worn book, we return to stillness. Your system continues quietly awake, humming in its protective rhythm. And you, listener, are free to drift into sleep, knowing that the logic, the layers, the care, it all continues without you for a little while. Thank you for joining us on this gentle exploration. This has been Byte and Night. May your dreams be peaceful and your thoughts beautifully structured.